This is a talk that I gave at any Scala, and I finished the important part of the talk in about 15 minutes. So if you guys don't have any interactions at all, this will be really boring, and we'll just finish in 15 minutes. But if you guys have a lot of questions, which I hope you do, then we'll run on sort of longer than that. So sort of audience-driven development. This is all going to be live coded. I'm going to sort of do things in an editor over here, I think. Hello world, print line. Hi. All right, this is your last chance to tell me that the font is unreadable or the color is unreadable, because otherwise we're just basically going to go with this. My name is Daniel Spiewak, for those of you who don't know. I work at a company called SlamData. Yay, that's basically me. I've talked about a lot of stuff, and today we're going to be talking about the free monad. So how many people here have heard of the free monad? Cool, like basically most of everybody. Now, honest question, and no aspersions, how many people here like really understand it? Awesome. This talk is for you. Like I really want this to be a like, come in with not understanding, come out with like, yeah, I get it, like 100%, we're good, right? You may not like it at the end of it, but like, you'll understand it. And if you don't understand it, mea culpa. And the way we're going to do this is the way that I learned to understand it. Because like, honestly, I even used the free monad for years before I really got it. And the way I got it was just implementing it myself, like just from scratch from an empty editor buffer. So what we're going to do is Command A, delete. We are going to implement the free monad starting right now. Cool? All right. So now what we're going to do, so what the free monad is a monad for any type constructor. So for any type constructor f takes a single type parameter, we're going to implement pure and flat map. So now remember, pure is that thing that takes an A and gives you, an f of A, where f is a monad. And then flat map is that sort of complicated thing that takes an f of A, a function A to f of B, and gives you an f of B, right? So you've got, lift something into the monad and then sequentially bind away. So our goal is to provide this functionality for any type constructor. And by any type constructor, I mean it's not just like option or list or like easy things like that. I mean like my random, completely unconstrained thing that doesn't even have A's inside of it of A, right? So like just completely random stuff. So can we actually do this? Well, let's see what we can do. So we're going to start off with sealed trait free of f. Let me give us another line there. So sealed trait free of f of A. Okay? So it's going to be the free monad for any type constructor f. And it's a monad, so it has an A inside of it, right? So we're going to have to do that. And we're going to have a flat map. Okay? So this is just part of what it means to be a monad, right? We take an A to a free of f of B, and we give a free of f of B, right? Everybody following me so far? This is exactly what we have to do. And we'll just like triple question mark that out for now. And I'll create a companion object here. And on this companion object, well, we already talked about how we need pure, right? So pure takes an A, and it returns a free of f of A. Okay, so this is the return function from Haskell. ScalaZ calls this point. Like I don't know, like whatever you want to call it. It's pure, right? Okay, so we have to define that function. And I'm going to add a third function to this mix here, just because I know the future, and I know what's actually useful here, which is, OK, we're going to call it lift m, OK? And it's, oh, actually, somebody correct me on type signatures here. All right, so we have to put an f of A there, right? By the way, because I'm a coward, we're not actually compiling this for real. We're just using the compiler of my mind, because that way my talk can't like flame out and like randomly fail. So if you see me like make some sort of like Scala solipsystem, like tell me. Because otherwise I just won't notice. All right, so lift m is going to take an f of A and put that into a free of f of A. Okay? This seems like a reasonable function to have, right? So maybe we already have something that's in f of A. We want to put it into the free monad. We want to get a monad for our arbitrary type constructor, right? So these are the functions that we are trying to implement. So let's see if we can do this, right? Let's start with pure. Okay? Pure seems like it's probably the easiest thing to do, right? So what can we do? Now, we'll notice that free currently doesn't actually have any structure, right? We haven't implemented any constructors for the free ADT. So presumably, we're going to have, like, down here, here be case classes, right? So stuff is going to be down here, okay? So pure. Well, we don't have any structure. We don't have anything that we can do with our A that turns it into a free. So probably the easiest thing we could do, maybe, is just add a case class. Pure of A contains an A, and it is a free of FA. Okay? So if we've got that, then this is really easy, right? Pure of A. Done. Cool. So okay, we've implemented one of our three functions, 30% done. What else are we going to do? Well, what about lift M? Okay, so lift M. Well, here's the first question we should ask, right? So we've got some structure now, right? Free actually means something. Can we take an f of A and put it into a free FA? Can we actually do that given the structure that we have? And the answer to that is no, right? Because if we tried to do something like pure of FA, this would actually end up being like free of f of like f of A or something like that, right? That's completely not what we want. So so we need to do something about this. So well, what can we do? Well, we can't do it with the structure we have. So let's just add another case class, right? Lift f underscore A FA extends free f of A. Okay, lift FA. All right, sweet. Okay, we're 2/3 of the way done, guys. Cool. Does anybody object to what I've done so far? It seems pretty uncontroversial, right? Flat map. Okay. So can we implement flat map for this thing? Well, we could probably implement it if we only had pure, right? So like pure, we get the A out of that. We could probably find some way to like turn it back into like a free of f of A. But the thing is that we also have this lift thing, right? And so we can't, the signature of flat map, right, requires us to provide it with an A. But if the free that is represented by this is just like, is a lift, then that lift contains an f of A. Well, we don't know anything about f. We don't even know if it contains an A. So how are we going to get that A to give it to the function? Well, answer is we can't. And there's sort of very elegant proof that we can't. So I'm going to learn how to type and import things. So what can we do here? Well, we can basically do what we've been doing so far. And we can cheat. Case class flat map. F, I'm going to call it E. And self is going to be free f of E. And then we're going to have some function e to free f of A, and that is a free f of A. Cool. So now we go up here, flat map this and f, right? That works. And we won't save because we're not actually saving, and that is the free monad. Applause? No, it's okay. This is super confusing, right? Because we didn't actually do anything. Like nothing is actually implemented here, right? We just like wrote a bunch of data and then called it a day. But honestly, like I'm not actually lying to you. This is the free monad. This is all there is to it. So obviously this is not useful, sort of in its current form, right? So maybe it might be nice to write a function that actually maybe does something with this data, something that's something other than a type constructor. Oh, by the way, just because I'm paranoid about the JVM, we'll do that final. All right. So what's another sort of function we could write here? Because we've already satisfied all of the constraints to be a monad. And by the way, this is a lawful monad, hilariously, right? Like this is actually like completely valid. No one will complain about this. So anyway, a function that's traditionally put on the free monad is something called fold map. Okay. Now the fold map function is a little bit tricky, and there's a reason for its name that we'll get back to in a second. But the fold map function says, okay, given some type constructor G, they're completely different than F, and that G that is a monad. Okay, so we have a monad for G, and a function called a natural transformation that maps from F to G, and we'll loop back to what this actually means in a second, give us a G of A. Okay? So there's a lot to unpack in this type signature. But what this is saying is we've got this free monad structure thing that has some stuff inside of it. Maybe a bunch of flat maps, maybe some lifts and things like that. Sorry, what? Where is the A from? The A, yeah, we're inside of free right now. Yeah, so the A is in scope. Okay, so we've got this free that has like some structure and things, and you know, it represents all of these operations. And we've got this other completely unrelated type constructor G that happens to be a monad. So we know that G is a monad. F is not a monad. G is a monad. And we want to sort of convert our free structure and sort of interpret it into G, and you know, given a way of actually converting the individual funcs. And what this allows us to do is it allows us to sort of defer the notion of interpretation. We'll get back to that in a second. But this is the function that actually does things, right? Because you know, we're not just going to like run, you know, create a new case called fold map and call it a day, right? You know, we're actually going to write this function. So before I do that, though, I want to be clear about what natural transformation is, right? So this funny squiggly arrow thing here, this is Scala Z syntax. If I write this in terms of cats, it looks like this, right? So that's maybe a little bit more familiar. So what function k is it's a function that takes two type constructors, or it's a trait that takes two type constructors, and it has just this like a can't type apply function that takes an f of a and returns a g of a. So a function k is just basically this notion of mapping between two type constructors, right? So for any f of a, or f of b, or f of c, or like f of anything, right? F of anything, we can get g of that same thing. That's what function k says. It's literally a function on type constructors, as opposed to a function, right, on types. Okay? So this is a really useful thing. So what we're saying is, given this natural transformation, you know, function k out to g, and the fact that g is a monad, we can do this. So how are we actually going to do this? All right, so we're gonna pattern match on ourselves and start implementing things, right? So pure of a. So what do we have, right? We've got an a, something of type a, and we need to return a g of a, right? Because that's what the type says we have to return. So how do we get our a into a g of a? Well, we know that g is a monad, right? And remember from earlier, one of the functions that monads have is pure, which takes an a and puts it in, you know, m of a. So we can take an a and put it in g of a because we have monad for g, right? Pure of a, and this returns a g of a, right? Everybody agree with that? Seem satisfactory? Cool. All right. So another case that we could have here is lift, right? So lift, I mean, this is an f of a inside of here, right? So we've got a lift. What are we going to do with that? Well, we have an f of a, and we're trying to get to a g of a. And we have this function k thing sort of handily here, which says for any f of a, I can give you a g of a. So we just call natural transformation on f of a. And this will return g of a, right? Cool? So far, so good. Nothing terribly complicated. All right, flat map. This seems like it'll be scary, right? So inner and f. Okay? So how are we going to do this, right? Well, inner is of type like free, you know, f of e, right? Where e is something complicated. I made it lowercase for a reason. And then f is like e to free of f of a, okay? So we've got to turn this mess into g of a. How are we going to do that? Well, we can't do anything with f just yet because we don't have an e. Right? This e is like this mysterious thing that comes from somewhere. The only place it could possibly come from is inner. So let's do something with inner, right? Well, what can we do with inner? Well, we can flat map it, but that's probably not going to help us. Because you know, if we just flat map it, right, we're just essentially back where we started. But the other thing we can do with it is we can fold map it. Okay? So if we fold map inner.fold map natural transformation, this is going to return to us a g of e, right? Everybody agree that those types work out? And that's not a rhetorical question, by the way. I might have just like simply made a mistake. So keep an eye out. This is the dangers of not compiling your live coding. So fold map natural transformation, that gives us a g of e. But can we take that e and like sort of do anything with it? Well, we know that g is a monad. And the two functions that monad have are pure, which we already used, and flat map, right? So maybe we can just like monad g flat map, right? I just put my computer to sleep, and that is fantastic. Ladies and gentlemen, the touch bar. Let's see if that comes back up. Cool. All right, note to self, disable that button. All right, flat map this, okay? And this is going to give us an e. Okay, so we've got this lambda now that will take an E from the flat mapping on G using monad G, right? So now we've got an E. What can we do with it? Well, we can call F. Okay, that's actually literally the only thing we can do with E because there's only one operation on it. So we've now passed this into our function. We're making some forward progress here, right? Because we've now used at least both of our parameters. But this is not going to type check because flat map on G wants the function that we pass to it to return a G. So this doesn't return a G, this inner thing, right? This returns like free of f of a, I guess, right? Yeah, free of f of a. So if only there were a way that we could turn free of f of a into g of a. And of course there is, right? So we just like take this thing and fold map it again, and now it works. So that's cool. So we actually have that. So this is a little dense, right? But like, is it clear what's going on here, right? So we're transforming the structure of our free monad, the structure of our so three things, right? Pure, lift, and flat map. We're transforming that and we're interpreting it into some other monad G, and then we're running that monad. And that's all that we're doing here. So this is the free monad. This is the whole structure of the free monad, and everything else that people traditionally do with the free monad is just built on top of this. We have now implemented the whole thing from scratch. And the cool thing is, like this f, there's no constraints on this f whatsoever. We could put anything we want into this type constructor, and or nothing into this type constructor, and this will work. There's nothing wrong with this trick. So that's really cool, right? Are there any questions about this? Does it make sense? Does it not make sense? Did I actually type it correctly? E flat map. What are you asking about? Inner has an E type parameter. That's correct. So yeah, so inner is this thing of type free f of E. So the reason, I'm being tricky here, right? But like this E thing here, right? The reason I called it E is because it's existential. Okay. So yeah, okay, you can all see this on the screen. So E, so you notice that E, like it's on the left-hand side here, it's like in this flat map thing, but I don't actually put it in sort of the extends, right? It extends free of A. So this is actually kind of this weird thing, right? Where like, you know, your E is sort of trapped inside of the subtype and then you sort of threw it away, right? In Haskell, we call this a phantom type or a gadget, right? So you actually need a language extension to do this elegantly in Haskell. In Scala, we just sort of call it object orientation, something, I don't know. Yeah, so the reason we need this is because we might have an instance of our free monad, say like free of f of int, right? And then we flat map on it, and now we've got a free of f of string, right? So we can sort of flat map things together, right? Because there's no constraint, because flat map is sort of A to f of B, right? So it's sort of like you're changing your type as you go along. But that's building up this free monad, this free structure, right? And remember, inside the free structure, all we're doing is like putting things inside of case classes, right? So we're not actually interpreting anything yet. So we have to hold on to all of those like individual types, if you will. So we hide them off in these existential E things. And then when we come along to fold map, we're like, well, okay, we've got this E. We don't have any idea what it is because we threw it out like 3 hours ago. But we know that it's the same thing as this other E over here, so we can put them together. So the type system actually holds us together. There was a bunch of bugs in Scala until very, very recently with respect to this particular language feature. And this didn't work until like about 8 months ago. So it's actually really nice that it compiles now. Good question, really good question. Anybody else? Okay, so we'll move forward because we have now, it has been 20 minutes, so 5 minutes longer than I expected, and we have completely defined the free monad and everything there is to know about it. So what we're going to do instead of just sort of hanging out is we're going to see how you use it. Because the thing is that now that you actually like see what the free monad is, and really honestly like how all of it works, there's no magic here, the examples of what you do with it kind of make a little bit more sense. So, new editor buffer, Scala, all right? Here is a very common use case for the free monad, right? So let's say that we have some part of our code that's doing something with a file system, okay? And like all good programmers who've been bitten by unit testing and integration testing in the past, we know that you don't really want to deal with the file system directly. You want to build some sort of virtual file system layer so you can actually test the thing and not have your CI randomly muddling up the file system. And there are frameworks out there for doing this, like Commons VFS and stuff like that. And they all more or less varyingly work horrifically poorly. They also are really specialized on this notion of a file system, right? And so if you don't have a file system, but instead have my cool microservice number 7, and there's certainly no mocking framework out there that will help you with my cool microservice number 7, you're kind of up a creek. So it's really cool to have a general technique for this, and this is what it turns out the free monad gives us. So what we would do with this file system thing is we would express an algebra of the operations that we want to perform on the file system. So here's what I mean by that. CL trait file system, or we'll just call it disk, right? Disk. And we're going to say disk of A. I have no idea what A is, but disk of A. Now object disk. All right. So one of the operations, each of the operations is going to become like a constructor on the disk algebra. So one obvious operation is reading. Okay, we might want to read a particular file off the disk, and when we read it, the result is going to be an array of bytes. Okay, so this is kind of the pattern that you use. You define your operations as individual cases of this algebra, and the algebra is something of A. And for each of the operations, the result type, the output of the operation, is what you put in the A. Okay? So the read operation is a disk operation of A. What about the write operation? All right, so actually I'm just going to all right, so write. So this is presumably going to also take a file name, right? Basically everything is going to take a file name. So it's going to take some bytes. And in this case, we're writing to disk. What do we want to return? Well, probably something like Boolean, but we're going to be dirty and just say unit, right? So all of our write operations always succeed. This is a very optimistic virtual file system, right? And then maybe you might have some other operation that's like delete or something like that, right? Thingy. Okay, extends. Disk, Boolean, I don't know, something like that, okay? This is really not that dissimilar from what we used to do with, service mocking, right? So where we used to say, okay, I'm going to have a disk service, and I'm going to have a way of reading from it. It's going to return array of byte, and a way of writing file string, right? You see what I'm doing here? So this is sort of like the old school way of doing it, where you define an interface, and then you're going to have different implementations of those interfaces, and then some sort of magical framework from the devil is going to inject them into your code. Rather than doing that, there's some advantages if we do it this way, and I'll get to that in a second. But this is sort of like the object-oriented equivalent of what we just did. Everybody following me? Anything doesn't make sense at all? Cool. All right. I see a lot of confused stares, but I'm assuming you're just in awe of how cool this is. All right, so so we've got our disk algebra, okay? But we can't actually do anything with it. Okay, we've described the operations, but we haven't actually described how you use the operations. All we've said is there are things in a sort of very philosophical way. The thing though is that by describing the disk algebra in this way, we can get some things for free. So disk is a type constructor, right? The disk takes a type parameter. It is an f of A, right? So we have this cool little thingamadoodle that will allow us to get a monad for any type constructor. So for any type constructor that takes a single type parameter, we can now get a monad. And it doesn't matter what's inside that type constructor, we can get a monad for it. So that's kind of cool, right? So disk M of A is free of disk of A, right? So disk M has a monad. Cool. But what does that actually buy us? right? I mean, we just finished seeing how the free monad basically has nothing inside of it. So like, why would we care, right? Well, it turns out that it allows us to write programs. Because what a monad is nothing more than just sequential computation, right? This idea that, well, first I do this thing, and then it gives me some result, and then I do this other thing, and it gives me some result, and then I keep, doing things, right? That's literally all a monad is. And we now have that structure for free. So what does it look like? Maybe we might want to write a program. So a program is going to be like, I'll use the full, rather than using the type alias, because I think it's hard to keep track of that stuff. So we're going to say free of disk of A, okay? And we're going to use 4 comprehensions for this. And we're going to say the first thing we're going to do is like read the contents of a file. So I'm going to say contents, right? So read the file, and the file is going to be like hi.txt, okay? Now read, of course, like this is a disk of array of byte. And what we actually need is a free of disk of array of byte. But that's like really easy to get, right? Free.lift m, I think we called it. Cool. Right? So now we have a flat map function, so 4 comprehensions will work. And then maybe we might want to do something like free lift m, like write hi2.txt contents, I don't know, plus array 1, 2, 3. Okay? That doesn't make any sense, but we're going to do it anyway. Okay? So we can write some disk contents, and we also want to like log the fact that we did stuff, right? So logs.txt did a thing.get bytes, right? Cool. And then I guess we'll yield int. We'll yield 42. So or some status code. Status code 0. Cool. That makes sense. That actually doesn't make any sense, but we're doing it anyway. So we've written a program here, okay? And this program does 3 things. Well, does in a relative sense. It reads a text file, or purports to read a text file, and then it gets some contents out of that. We have no idea where these contents are coming from, but this is totally like contents is really like legitimately of type array of byte, and we can like use it to do things with. So presumably it's coming from somewhere, right? So we get the contents from this file from somewhere, and then we keep like using it, and we write to 2 files, and then we're done. Okay, that is our program. But of course, it's not actually like doing anything, right? So just like the free monad, there isn't actually anything happening here. We just put some stuff in like data constructors, and then claim to be writing code. But in reality, like nothing has actually happened. So how do we make stuff happen? Well, the trick is in that fold map function. Okay. And by the way, I'm just going to call this. I'm going to make this a val because there's no reason for that to be a def. Yes.
Do you have to yield more than 0 here?
Do I have to yield more than 0?
More than 0. Shouldn't you be yielding the free monad?
Shouldn't I be yielding a free monad? Didn't mean to cut you off. That was technical glitch. Okay. No, I can actually yield whatever I want here. So the yield, I don't know how familiar you are with Scala's 4 comprehensions, but like yield basically is like map. It's not like flat map. So we can just like put whatever we want in here as long as it matches up with this type. So there's actually no reason that we're yielding int. I mean, really, if you were actually writing this program, you would probably yield unit. So we can do whatever we want. If we needed to yield something that was inside of free, like maybe let's actually make this more complicated, right? So like delete has to like delete something, right? So like maybe back, right? Free.lift m delete badness, right? Or delete evil, right? And then we could yield this. And now it's going to be like this is going to be a program that yields Boolean. That's probably a lot more useful. Good, good. Excellent question. Anybody else? OK, moving on. So we've got our program here. It's not actually doing anything, like I said. But we presumably want to make it do something. So how can we make it do something? Well, we've got this fold map function, right? So the fold map function says if we can tell Scala how we can turn a disk into some other type that has a monad. I'm just going to like do that because this is getting absurd. If we can tell Scala how we can turn disk into some other type that is a monad, then fold map can run our program inside that monad, and we'll get the results. That kind of sounds like more or less like we might want, like something we might want. So can we find a monad that makes sense to turn disk into it? English grammar is terrible. So it turns out that probably the most useful monad that we could use this with in production is a monad that actually, I don't know, manipulates the file system, right? Like something that actually runs our program. Whenever we're talking about like manipulating file systems or like reading from network sockets or launching missiles, you should be thinking at that point of the I/O monad. Okay? So the I/O monad, like the name comes from Haskell, but like this exists in various libraries. And I opened up a project literally this morning to add it to the cats library. So like I/O is basically everywhere, right? So I/O is a monad. And it's like I/O of A, so the result that it returns. So can we find a way to maybe turn disk into, so any disk of A into an I/O of A? Well, it turns out that this is pretty easy. So what we're going to do is we're going to represent this as a natural transformation, right? A function k from disk to I/O, okay? Equals new function k disk I/O. I actually want the Java 7, sort of thing syntax. It's sort of unfortunate that Scala can't always type in for this. All right, so def apply, right? And this is going to give so we need to take a disk of A, and we need to return an I/O of A, okay? For whatever A the disk decides to give us. This is the type that we have to define, all right? So how are we going to do this? Well, let's pattern match, okay? So disk of A. Well, what could we possibly be looking at? Well, possibility number one is a read. Read this file name, okay? And so given this, we have to return an I/O of, array of bytes, right? Cool. So that's actually not all that difficult to do, right? We just literally write the function. So like file, new file input stream, da-da-da. OK, actually, this is kind of difficult to do. We're just going to pretend we did all of that. So pretend that we just did like messy I/O stuff, and it went into this like I/O thing, and we returned an I/O of bytes. Cool. All right, we're done. What about write? Okay, write. We take a file and some bytes, and now we have to return. So write, remember, write is a disk of unit, right? So we have to return an I/O of unit here. So this is going to be like new file output stream. OK, this is actually kind of hard too. Basically, anything dealing with Java I/O is very unnecessarily hard. Cool. All right, so delete file. I think this one will actually be somewhat easier. All right, so here now we have to return an I/O of Boolean, right? So how are we going to do this? Well, this is literally going to be like, I think, new file and then file.delete, right? There, finally a function that we can actually implement. I hope that we can actually implement that. All right, cool. And that's all there is. We don't actually have to write anything else, because these are the only three possibilities for disk, right? If someone hands you a disk, it has to be one of these three things. So that was actually pretty easy. We just basically defined how this implementation was going to go. If you sort of rewind this back into object-oriented terms, right? And remember with like our sort of magic Spring injection service thing that we were talking about, right? This is sort of like the concrete implementation of your interface. Right? So this is your production implementation. This is the one that you're actually going to run your program with. So now we've got this natural transformation. We now know how to turn a disk into an I/O. And I/O is a monad, which means we can take our program and fold map with our natural transformation, and that's going to return an I/O of Boolean. And we can run that. And magically, sort of out of the blue, we've somehow gotten a running program, something that we can actually do that I don't know, feeds our family. That's pretty cool. Like just sort of like not doing anything at all. So programming is hard, guys. Yeah. So anyway, are there any questions about what we've seen, like what we've done so far? Nothing? OK, cool. Because we're about to get to this. We're about to get to the part where this gets really, really, really cool. Because the thing is that the whole point to all of this is testing, okay? The whole point to, and arguably, I would honestly argue, I would stand up here and argue that the whole point of functional programming in general is testing. Yes?
Just one quick question. The free lift hand, like on the right calls inside of your program, is there any syntactic sugar any way by abstracting that away?
Is there any syntactic sugar for abstracting away the free lift m repetitive madness stuff? Yes. So What people generally do is they'll do something like this, and they'll create a smart constructor. So we'll say like read with a lowercase r, and that'll return free of disk of array byte, right? And then you normally do like free lift read file. And then if you go down here, it becomes like a lot easier because you just, oh, well, I did the wrong one, but you just usually do like read, right? Okay, that's usually what you end up doing. There's various libraries that have tried to make that even a little bit better, where they'll just like derive that function for you. So then, like I wrote a library once where you could actually do this, and it just like magically inferred everything, and it was super cool, and it like crashed half the time, but it was cool. It was like, it was exciting, and nobody actually liked that for some reason, but it was cool. Yeah, no, it is. The boilerplate can be annoying if you're not careful. Yeah. Implicit def. Where is what? Line 6. This is a def. Yes. So I'll just space that out so it's a little easier to read. Is that clear? Oh, implicit def. No, it's not an implicit. That would be a little strange because so anytime you see implicit def, alarm bells should be ringing because it's like, well, shoot, am I accidentally getting an implicit conversion, right? Because you don't want implicit conversions. And this will in fact be an implicit conversion from string to like free of disk array byte. And that doesn't make any sense, right? Because anytime you have an implicit conversion from A to B, what you're actually saying is, well, A is sort of secretly a subtype of B, but like Liskov substitution principle doesn't make any sense here. So we definitely don't want that. But yeah, no, we want a def. There are some cool things we can do with implicits though, just not in a 1 hour talk.
Is it absolutely necessary to have an ADT for your natural transformation? Like if we didn't make disk sealed and you just have like the default case that said it returns an I or nothing, does it all work?
So is it necessary to have an ADT? And could we? It's not at all necessary to have an ADT. I'm just not sure what else you would do. So we could. I mean, so I guess for example, like.
If this was not my code,
oh.
so I just wanted to
yeah.
free Monad and make a natural transformation.
Yeah, so if this were not your code and you didn't know that disk was sealed and you just wanted to like use the free monad to do cool things, you can do that. And in fact, you could use the free monad to do a lot of things that have nothing to do with monads or programming. So this is actually where things get really, really, really crazy. So like I said, I work at SlamData. SlamData, like one of the employees of SlamData builds a library called Matryoshka, which is like the Russian doll, right? And Matryoshka provides some tools for abstracting over recursion schemes, which are like hilariously mind-bending things. So basically, like I know very, very little about them. But these mysterious things that I have to work with every day, and I just sort of go in and I'm like, I don't know how this code works, please help me. But one of the things you can do is you can use the free monad to abstract over sort of injecting things into holes in data structures, right? So we have these like trees and graphs, but rather than actually representing them as recursive data, we represent them as very flat data, where each like piece of the data has a hole in it. And then the free monad will just sort of inject things into there. And so when we sort of like expand it out, right, it actually becomes a graph at runtime, but we don't see it as a graph, and we just manipulate it as a flat structure. So it's actually cool. Like we don't write recursive structures or recursive functions anymore. We just like have recursion schemes. It's really bizarre. I don't actually understand it, so please don't ask me about it. But like, I'm still like, I am very much still trying to learn that. But hopefully someday I'll be able to give a talk about it and sound cool. Good question. Anyone else? Okay. We're not going to go that much longer. All right. But I wanted to talk about testing, because testing is like the reason that we do all of this stuff. It's the reason that the free monad exists. It's really the reason that functional programming exists. Because like functional programming is basically a response to the fact that all of us are really stupid. Like I am not smart enough to understand like software at all. Like I can't be a programmer. And so because I'm so stupid, I have to like restrict the domain of things that my code can do to like these immutable things that I can actually reason about, because my mind is sort of that tiny. And in order to do that, like functional programming helps me. And reasoning about code is basically the same thing as testing it, right? Because if you can reason about something, you can express that reasoning as a test, or as a property, or as a law. And then we have tools that can verify all of these things for us. So it helps us write safer software. So the free monad helps us do this. But it helps us do this on things that are not pure functions, right? My complicated business logic that talks to 7 different microservices and like brings some data back and like jumbles it up and then compares whether or not it's less than or equal to 7 because like some salesperson was like 7 is a cool number. Like that is not a pure function in any sense of any universe, right? But the reality is that's where most of our bugs are because the salesperson was crazy. So like how do we test that, right? The free monad is the answer. So you write that complicated logic in the middle in terms of the free monad, right? So all of these different services that you talk to, you represent them as algebras that are like this service, supports these operations, and I can get a free of that. So the question is, how do we take this and how do we test it? Okay? And the answer is, well, we can just write a different natural transformation. And there are actually better tools for doing this. They're just not open source right now, and I really, really hope they're open source soon. But I promise you they exist. But right now, what you do is you write a natural transformation. So rather than interpreting to I/O, which is like this scary thing that manipulates the disk, maybe we could interpret to like, val mock, sort of an odd name, but we can use it. Function k disk to like, well, now we're going to get into like strange land, but like, some like thing that's like, there we go. All right, question mark. All right, nope, I misassociated that, question mark. Okay, do these question marks make sense? I just realized that I did not at all explain that syntax, like in any sense of the word. The question mark here, this is, oh no, I did do it right the first time. All right, this is a compiler plugin called Kind Projector, and it basically avoids the need to do like crazy, sort of like question mark, bracket, type, lambda, alpha equals like this craziness, right? Hash lambda, right? No one wants to see that in their code, so Kind Projector eliminates that. All right, so we can write a function k that interprets from disk to the state monad, where the thing that's inside of our state monad is just like a map from string to array of bytes, right? So this is this notion of like an in-memory file system, right? We can define what that means, and then we can run our tests like in memory, just by saying, well, use the mock natural transformation, don't use the real one, okay? So this is like, you can think of this, again, like you can think of this a lot like a form of dependency injection that doesn't involve any magic and actually just uses monads rather than spring. Spring greater than monads. Less than monads. So anyway, but like that's really cool. And there's a lot of more powerful tools that you can build on this because inside of free, like fundamentally, remember, the implementation of free is really, really, really dirt simple. And it's data. It's not like complicated, sort of constructor injection inside of class loaders with sort of JVM agents or anything like that. Like we can't understand. It's actually data. We have it in our hands. We can introspect it. We can write other functions other than full map, right? These constructors are open, so we can just like sort of go into them and munge around and see what's here. And fundamentally, all we have is like just a list of actions, right? Sort of a sequence of actions that we're going to perform, a sequence of flat maps. We could go in there and we could pull that apart. And we could say, well, I want my function to say a read, followed by a write, followed by another write, followed by a read. And we could write that test. So for example, on a previous job, I wrote a test for a service that was talking to a database that shall not be named Cassandra that has compare and swap operations, right? And like atomic operations for some reason. And I wanted to make sure that my complicated compare and swap semantics were actually correct, right? Has anybody ever written a unit test for a cast loop? Like a compare and swap thing? That is like murder. Like how the heck do you unit test that? You're unit testing a race condition. That doesn't even make sense. But with the free monad, I could do it because I said, well, I'm going to set up this situation where it's like, I want to see my function read from the database first, right? So get some data out. And then I want to see my function compute some value to write. And then I want to see it try to write it. And then I want to see that write fail. And I want to see my function read from the database again to figure out the race condition. And then I want to see it try to write again. I want to see it fail a second time. And I can actually set that whole thing up and I can test it. And the function was bulletproof. Like I had a compare and swap like race condition test function that was bulletproof and deterministic. That's fantastic, right? That's how you write good software. And the free monad allowed me to do that. So Anyway, we're very much running out of time. At least if we take my artificial limit of like not an hour. So, are there any questions about things? I know I sort of hand waved past the testing thing really fast. But any questions at all? Anything you want to see again? Any like stuff? Do you want me to explain why a monad is a monoid in the category of endofunctors? Because we could do that too. Yes.
Hi. So I'm very confused in a good way.
Sweet.
I'm coming from a closure background. I don't know Scala at all, so I'm probably not the right audience for this. But I'm just so confused. I don't know. Like my brain is still trying to figure it out.
Sweet. That's great.
So if I had one question, it would just be, what? Like explain more of what the free monad does. Can you give me just some more concrete examples of the free monad in use?
Okay, so let's do another really quick concrete example, right? So rather than disk, let's imagine that I had like some service, right? That was like weather, and my weather service, and I'm just creating an algebra for this, right? My weather service has the ability to like get weather for some zip code, and that returns weather of temperature or something, right? And I'm just like describing the operation. So I'm not actually implementing here. I'm just describing. It's sort of like writing an interface, except instead of writing an interface, I'm producing data. Okay? I'm describing what data could be here. Right? We have get weather and like get forecast, and this is like 5-day or something like that. Like I can sort of produce these operations, right? So
each one of these case classes would be like an endpoint on some theoretical API.
yeah, each one of these case classes is like an endpoint on a theoretical API. And that's actually a very common thing to do. When you're writing some messy business logic here and you've got like 6 microservices that you're talking to, just write an algebra for each microservice, right? And that describes how you can get them into data. Now what the free monad does, and all that the free monad does, is it allows you to write sequential programs with that data. Okay? Because this is all that monads are, right? They're just sequentialization, sequential computation, right? So the free monad gives you sequential computation for any data at all. And so that way we can just describe our DSLs, like our operations, in terms of data, and the free monad gives us the computation stuff. It's like basically factoring out boilerplate in a way. Okay. Does that help a little bit? I'm going to have to not do more of the example because like if I sort of keep going down that rabbit hole, we'll have to be typing for a lot longer. But I can show you more if you want to come up to me later. Okay. Yeah, cool. Confusion is good. Anybody else confused? Yes. Okay, multiple people come up, and I will show you examples later. Maybe this was just like a terrible talk, and like the whole room shuffles forward. It's like you didn't explain anything, Daniel. Yes. Wait, there's a microphone.
Oh, thank you. In Scala today, is there any way to combine this with software transactional memory or something like Haskell's atomically?
So there's some people who've played around with that, and actually there was a discussion in the CATS channel like an hour ago about that idea. Software transactional memory is really interesting, and you could very definitely describe operations on it using the free monad. That might make a lot of sense. Generally speaking, I find though that STM doesn't make sense. Like I just in practice, like it doesn't actually get used all that much, which is really kind of weird. Like it seems like this cool thing, but I've never actually seen someone do something useful with it. If you are someone who has done something useful with STM, please come and show me, because I'd like love to see it. But I've never actually seen someone do anything with it. But yeah, you could. I've actually seen people do things like use the free monad with something that's already a monad, just so they can get like sequentialization, but not sequenced inside of the inner monad, and then sort of delay their computation. That can kind of be cool.
So yeah, I'm new to free monads, but the thing that's kind of interesting to me is that it seems like these are mechanisms to basically allow you to have arbitrary sequential computation, basically encoded as data and interpreted the way you want to. So it feels like you could take an arbitrary procedural program and write it this way, or even a translator, to translate it into this functional stuff, right? So it's almost like the Lambda is the ultimate go-to type thing. It's kind of like you can basically go ahead and mimic go-tos with continuations and all these other things. So is there a sense among people using this that this is not the first thing that you reach for? Because it seems like, at least at the if you can end up having functional code that looks exactly like procedural, what's the advantage really? You know?
Yes. Okay. So there's a couple of things packed up in there. That's a really fantastic series of thoughts, right? And like your initial description of what the free monad is, that's exactly what it is, right? So why would you do this rather than just procedural code, right? Well, the thing is that like a procedural.
Why would you do this rather than trying to find a more functional solution, or one that is more functional?
Yeah. Well, what is a more functional solution, right?
Well,
I mean, functional, right, is just like immutable. So the whole idea behind it is trying to get something that's easier to test, easier to reason about. And what this does, like all that the free monad does, is it gives us the ability to sort of peel apart sequential computation, sequential programs, and see them as data, right? Whereas when you have something that's sequentialized but not inside of a structure like this, where it's all as data, then you can't see what's happening, right? So if you just have function composition, for example, you can't go in the middle of that and see, well, I really want to be sure that F happened before G. You can't actually like say that. You have to look at the endpoint and say, well, I guess the answer is 42, so maybe that's right. So that becomes harder.
I guess the thing is basically I'm used to working with like Haskell and like lazy and stuff like this, and you're kind of like, there are many things that don't have to be sequential, right? It's just, when you're dealing with the outside world, quite often you want to have sequential computation. So maybe that's the place where you just don't reach for this until you really need it? Or?
Yes. So this is an important question, right? It's like, where does the free monad make sense? Because in the small, in functions like taking the absolute value of a number, right? There's no reason whatsoever to put that in the free monad. That makes no sense, right? Doing some sort of computation, something that's actually like already pure. Why would you put that in the free monad? And at the other end of the spectrum, maybe you might want to have something complicated like I'm running this on a web server, or I'm setting up some sort of like asynchronous socket poll or something like that. Why would you put that in the free monad? That doesn't make any sense. I mean, maybe it does make sense, but like probably not. Like you're dealing with like concurrency, you're dealing with I/O, you're dealing with like really like raw bits. Like I don't know, but like that middle part of your software stack, where you're doing things like the crazy business logic, the talking to 7 services and like stuff underneath it. Maybe that's pure functions or like some sort of messy I/O thing. But like your middle stuff here is complicated logic, but it's like middleware stuff. And you want to be able to write tests about that middle stuff as easily as possible, because honestly, like that's where bugs in software are, because that's where all your edge cases are. So the free monad. Like without the free monad, you would have to write that stuff in I/O, because you're like doing service calls and stuff like that. But I/O you can't test. Like that's an integration test. Free monad you can test, so that's the advantage. Yeah, excellent, great question. Basically out of time, I think, almost out of time. I don't know, no one's pulled me off the stage. Last question? No last questions? Cool, thank you very much.